This video is all about the double angle identities. These are really important identities that you need to know. Just in the same way as you need to know that sine squared plus cos squared is 1, and tan squared plus 1 is sec squared, and cot squared plus 1 is cosec squared, you need to know these ones as well. These are your new times tables for the rest of your A-level maths. When you see sine 2x, you need to know that that's the same thing as 2 sine x cos x. When you see cos 2x, you need to know that you could write that in 3 different ways. We could rewrite it as cos squared x minus sine squared x. Or, if we wanted to, we could rewrite it as 2 cos squared x minus 1. Or we could write it as 1 minus 2 sine squared x. So depending on the situation, there's 3 different ways we could write cos 2x. And then tan 2x is not quite as common as the other ones, but that is identical to 2 tan x over 1 minus tan squared x. So make sure you've got those copied down, make sure you've put a big box around them. You need to learn them. Let me show you where they come from. So these are the addition formulae as they are given to you on the formula sheet. Sine A plus B is equal to sine A cos B plus cos A sine B. What I'm going to do is I'm going to swap the A for x, and I'm going to swap the B for x. So that would give me sine x cos x plus cos x sine x. The left-hand side, the x plus x here is obviously just 2x. So sine 2x is equal to. Now notice that these two things here are exactly the same. It doesn't matter which way round we multiply numbers. So I could flip the cos x and the sine x around. To be sine x cos x. And now you can see hopefully that these are the same. These are like terms. And therefore those two can be collected together to be 2 sine x cos x. And this is the first of the double angle formulae we looked at on the previous page. Similarly with the tan, again if I do the same thing, if I let A be x and B be x, then I would get tan x plus tan x over 1 minus tan x times tan x. The tan x plus tan x is 2 tan x. And the tan x times tan x is tan squared x. And so this is the tan 2x formula that I showed you a moment ago. And then for the cos, same idea. A is x, B is x. So I would get cos x minus sine x sine x. So the cos 2x is equal to cos x times cos x is cos squared x. And then the sine x times sine x is sine squared x. So that was the first of the cos addition formula, cos double angle formulae I showed you a moment ago. But do remember that we also know that sine squared x is the same thing as 1 minus cos squared x. So I could, if I wanted to, swap this for this. So I'd get cos squared x minus the 1 minus cos squared x the double negative would become a positive. And notice now we've got cos squared x plus cos squared x, which is 2 cos squared x with the minus 1. And that was the second of the cos double angles I showed you a moment ago. Alternatively, instead of me changing the sine squared, I could have chosen to change the cos squared, because I know that cos squared x is the same thing as 1 minus sine squared x. So if I swap this for this, I get 1 minus sine squared x minus sine squared x is 1 minus 2 sine squared x. And that's the third of those double angle formulae. So, those are the double angle identities. And that's how you prove them. Let's have a look at a few examples of using them then. So here I'm asked to prove that 1 minus cos 2 theta divided by sine 2 theta is identical to tan theta. First thing I've done is I've rewritten the sine 2 theta as 2 sine theta cos theta. That's the only way I can rewrite that. Notice that I've left the cos 2 theta as it is for now, because I wasn't entirely sure how to rewrite that one. Because there's 3 different versions of it, as we just saw. So let's now have a think about what we could do with that cos 2 theta, which would be the best of the identities to use. Now in this case, we're trying to end up with tan theta, which I know is sine over cos. So I would quite like to have sine on the top of my fraction. So I think that the 1 minus 2 sine squared version, remember this is the same thing as this, I think that will probably be the better option in this particular situation. Right, let's simplify that numerator. We've got the 1, we've got the minus 1 and the minus minus. And now I notice the 1 minus 1, so that's just 0, that's going to cancel out. Then I notice the 2 on the top and the 2 on the bottom, they're going to cancel out. And then I notice the sine on the bottom and the sine on the top, they're going to cancel out. And we'll be left with sine over cos, which I know is identical to tan, which is the right-hand side. So by thinking carefully about how to replace the cos double angle formula, looking at what I'm aiming towards, giving me a clue as to put the sine on the top, helped me to solve that problem. Next example. I needed to prove that 2 cosec 2a minus cot a is identical to tan a. So starting on the left-hand side again, because there's more things for me to do here. The cosec, I know that's 1 over sine. So in this case, I will have 2 over sine 2a. This is the same thing as this. The cot A, I could write that as 1 over tan A, but considering I've got this in terms of sine, I've instead chosen to write the cot A as cos A over sine A, because it's going to allow me to combine it with this more easily. The next thing I've done is I've expanded the sine 2A with the double angle formula. Sine 2A is the same thing as 2 sine A cos A. Then I notice that these 2's are going to cancel out. And then the really important next step for me to simplify this stage here, I've got two fractions, I need a common denominator. I've got a sine A cos A here, and here I only had a sine A. So I'm going to multiply top and bottom here by cos A, so that I get a common denominator. And hopefully you can see that's where this cos squared on the top has come from. We've now got a common denominator, so I can now bring these two fractions together as a single fraction, with the 1 minus the cos squared A on the numerator. I know 1 minus cos squared is sine squared. And then I notice that the sine on the bottom will cancel one of those sines on the top. So I get left with sine A over cos A, which I know is tan A, which is the right-hand side. So we're done. Part B of this question said hence. Now that's a really important word, especially for this topic, because what that's doing is that's telling me to use what I've just done. So using what I've just done, I need to solve between 0 and pi over 2 the equation 2 cosec 4 theta minus cot 2 theta is equal to root 3. Now to do that, I need to think really carefully. I'm going to clear a bit of space, hopefully to make it a bit more obvious. I need to think really carefully about how this links with what I just did. You might be able to see it just by looking at it. I'm going to write it underneath to help the comparison. I've got the 2 cosec 4 theta minus cot 2 theta. I can see this is the same as this. I can see this is the same as this. The only difference is that A became a 2 theta. And if A was 2 theta, then 2A would be 4 theta. So the only difference here is that instead of an A, it's a 2 theta. So what that means is I can replace all of this with tan 2 theta. Now the rest of this question is really easy, because I can just do tan inverse of root 3 to get the pi over 3. I've then drawn my graph to check the next solution. I know this is pi over 3 here, so the next answer will be pi plus pi over 3, which is the 4 pi over 3. And then I've divided both of those answers by 2 to get theta. Pi over 3 divided by 2 is pi over 6. And the 4 pi over 3 divided by 2 is 2 pi over 3, which is actually too big. That's outside of the range, so I'm not going to give that solution. This question asks me to solve for x, the interval between 0 and 360, cos 2x plus 3 sin x is equal to 0. So what I did is I looked at the cos 2x really carefully, and I thought, do I want this to be cos squared minus sin squared? Do I want it to be 2 cos squared x minus 1? Or do I want it to be the 1 minus 2 sin squared? And I chose the third version, because I wanted it to match up with the sign in the original equation. Because now we've got a nice, relatively simple quadratic equation that I've rewritten in this form. I've then used the quadratic formula to find that sine x will have to equal 1.78 or minus 0.28. I know this can't give any real solutions because it's bigger than 1. When I did sine inverse of the minus 0.28, I got minus 16.3, which on my graph is down here. So the other answers that I do want inside my range are there, which is 180 plus 16.3. And here, which is 360 minus the 16.3. That one's not in the range, these two are. And last example for this video, I was asked to prove that cos 3x is identical to 4 cos cubed x minus 3 cos x. So I'm going to start this way in the same way that I proved the cos 2x formula, with the addition formulae from the formula sheet. This time though, instead of having a and b as x, this time I'm going to have a as 2x and b is x, because that's going to give me the 3x that I need. So replacing a with 2x and b with x, a with 2x and b with x. Now I know cos 2x can be written in different ways. This time I chose the 2 cos squared x minus 1. And the reason why I chose that is I looked at the answer and I saw I wanted it in terms of cos, not sine. So that's the reason I chose that version of the formula. The sine 2x, I had no choice about that. I had to write it like this. Next step, expand the brackets. So the 2 cos squared x times the cos is 2 cos cubed x. The minus 1 times the cos x is minus cos x. I then noticed I had a sine x and a sine x being multiplied together there, so I could write that as a sine squared x. And that sine squared x, I've then turned that into a 1 minus cos squared x. And again, the reason for that is I want it in terms of cos, not sine. And I know that sine squared is equal to 1 minus cos squared. I was then able to expand these brackets, so the minus 2 cos x times 1 is minus 2 cos x. The minus 2 cos x times the minus cos squared is positive 2 cos cubed, which I then collected together to get 4 cos cubed minus the 3 cos x. And so this is an identity for cos 3x. So, remember these double angle formulae? How you can prove them using the formulae on the formula sheet, and then the different ways you can use them to either prove identities or solve equations.